So, Chapter 8. We're on Chapter 8. We're going to discuss hypothesis testing, which will lay the groundwork for the rest of the semester, where everything else we're going to do is hypothesis testing. And we're going to go over basically the hypothesis test equivalents of the confidence intervals that we've done in Chapter 7, except we're going to preclude it, prologue it, prepend it. We're going to have this in the beginning, the basics. So we're going to lay down the foundation for hypothesis testing. All right, so a hypothesis test is a claim or a statement about a property of a population, a hypothesis. And then the idea behind making a hypothesis is that you usually want to test it. And so we come up with this idea of a hypothesis test. Sometimes it's called a test for significance. I'd like to think of it as a step-by-step process of testing a claim about a property of a population using a sample. I was talking to a statistician once and said, one of the hypothesis tests is one of those things that's really just a recipe. And really, that's all it is. In math or in computer science, they call it an algorithm. Algorithm is a step-by-step process to solve a problem. It's exactly what it is, and if you just follow the steps, you'll be fine. After a while, you can skip around the steps once you get a feel for what's important. But I think in the beginning, it would be a really good idea to follow through the steps. There'll be 8 steps in total, and I'll list them all down in a file, and then try to break that down. Or usually I'd like to look at it as a big picture broken down first, and then we'll list down all the 8 steps, and then we'll fill in the blanks of what those steps actually mean. Now, this rare event rule we've already talked about when we were back in Chapter 5 when we started study distributions. And I think this is an example that I've alluded to in the past few lectures, thinking that this slide will come up, the next slide will come up, but it hasn't. So it's finally here where we get to talk about the rare event rule and hopefully in a meaningful way. And it's talking about the probability being so small that we can probably assume that there's something else going on aside from basic probability that's happening. All right, I think this is an example. I have a lot of words here. It's basically that company that kind of pushes a pregnant woman towards having a boy or a girl. We've talked about that company already. And it says here that this company called Gender Choice kind of increases your chances of having a boy or a girl with your choice. And so let me start with this suppose statement over here. Suppose we conduct an experiment with 100 couples, just to make it easy, and this is a good way to picture it, who want to have girls. All these 100 couples want to have girls, and they go through the Gender Choice easy-to-use in-home system described in a pink package. So for the purpose of testing the claim, an increased likelihood for girls, we'll assume that gender choice has no effect. So that's your assumption. Okay, you don't believe that company. They don't have any effect on the gender of birth or whatever. So let's take a look at scenario A here, where 100 couples go to this place and these 100 couples want girls for their babies, and so they get this special package. And then out of those 100 couples who've had a baby, 52 of them were girls, and 48 were boys. So based on that result, what can you say about this company? Does it look like you got more girls, right? Out of 100, you got more girls than boys. So do you think this is an effective product? No, it doesn't seem effective. Just because there's a little bit more, it leaned towards the girls. Just because there's a little bit more girls than there were boys doesn't mean it's an effective product. Because having 52 girls out of 100, what's the probability of that happening? Well, we can use binomial distribution to figure that out. But it's a pretty high probability. Out of 100 girls, or out of 100 babies, 52 of them were girls, where there's a 50-50 chance of having a baby or a girl. Then there doesn't seem to be anything extra happening with this company. They don't seem to be doing anything special aside from giving you an easy to use in-home system in a pink package, because 52 girls is just about normal, or we would call it in our class a usual value. So there's nothing going on there. So if that was the case, where you only had 52 girls out of 100, that's really close to 50. And so really you can conclude your initial hypothesis to say that there's nothing going on here. It's not effective. There isn't sufficient evidence to say that this company is effective in coercing the baby to be a girl versus a boy. Does that make sense? That was a little over 50%, but it's the fact that it's only a little over 50%. It's not that big of a deal. Now, let's go back and look at this scenario. Suppose you did the test on this company and there's 100 couples who wanted babies, and then so they all want girls, and those couples got this easy-to-use in-home system in a pink package, and 97 of those babies were girls. What can you say about that? That's pretty rare. It's kind of rare to have 97 girls out of 100 babies, right? It's 97% chance. That's a pretty high chance. And, you know, out of 100 births, we would expect about 50 babies, certainly not 97. So in that scenario, that is a rare event. So this is the rare event rule. Something that has a probability that's so small to actually happen means that there really must be something going on with that company. They must be doing something to have these statistics pop up. They must be doing something to the fetus, to the baby that's in incubation, where they're I don't know when you would deal with this. I'm assuming before you get pregnant. I don't know when prior to conception. Yeah, because that's what happens, right? In conception is when the XY, and it's up to the male. So maybe this package should. I don't know. I still haven't researched that. Maybe we should check that out if that's actually real. Anyways, So this is where the rare event rule applies, where there's something that you would, probability-wise, you wouldn't expect this to happen, but it did happen, so there must be something going on there. There must be something that they're doing to actually make these babies to be girls, instead of just having a random occurrence. Okay? So we're going to take that idea, this rare event idea, this really small probability idea, is something that we're going to look at towards the end of today, and we're going to eventually call it a probability value. And if we have a small probability value, then we're going to say that there's something happening with that situation. It's not just per chance that this sample gave us this piece of information. There actually must be something going on, and that's the whole gist about the rare event rule. All right, hypothesis test. I think this is where I want to start off with a blank page. There are 3 basic keys to a hypothesis test. I'm going to make a 2-column panel here. Maybe later on it'll become 3. I think I want to insert a table. There's 3 main steps. The first is to state your hypothesis. And identifying your hypothesis in itself is going to be a little tricky. And in identifying your hypothesis and stating your hypothesis, we're going to break that down to like three steps or so. So that's what I'm going to use the second column for. The second major step is to test your hypothesis. And then the last step is to make your conclusion. About your hypothesis. So in that baby example, what we can say is that we'll go back to that Word file in a minute. What we could do in this example is we can use this as an example of how we're going to state our hypothesis and what we're going to say about it, and you know, that kind of example that we're going to set up. And so in doing so, when you build your hypothesis, what you're going to come up with is the idea of a claim, a statement about your problem, the specific problem that you're dealing with. So let's take a look at this example and kind of build upon this example. Where let's take a look at the example where we have 97 girls. So this sheet, by the way, this page will be posted up as one of the notes that you can download eventually. So if you're having a hard time trying to keep up with the notes, don't worry about it. I'll post this up. So in stating your hypothesis, it has to be done in a formal way, so that we're always going to be testing a specific type of statement. Okay, and before we get there, what we need to do is we need to come up with like I said, an algorithm or a process. And so this is where the step-by-step process of the hypothesis testing is going to happen. and I'll actually label it step 1, step 2, step 3, etc. So I want to make sure at this very early stage that when I say hypothesis and claim, those two may be the same, but they may be different. Okay? A claim is a statement about the problem that you're trying to study, and a hypothesis is going to be specifically a statement that would fit into this step-by-step process, this textbook recipe, whatever you want to call it, algorithm, and your statement has to be in a specific form. So your claim has to be, in this chapter at least, we're going to look at our claim as a parameter that you're testing. So in chapter 8, let's be a little bit more detailed. I don't need to use population here, but I want to kind of make sure that it's clear that what we're doing is a population parameter. So in this chapter, in chapter 8 specifically, your claim is going to be a comparison between a population parameter and a number. So your claim is going to be about a population parameter that's compared to a number. And when I say compared, we're going to use, the equals, the equality, the inequality business. Okay? So, if we were to do this as an example, what could be a claim here in this example? It has an effect, so the gender choice has an effect, and you got this pink packages. What can you say about this this particular scenario? What would be a good example of a claim? That it has no effect? Okay. Okay, so when you say that it has no effect, what does that mean kind of on the statistics side? I want to pick a parameter, a population parameter, that focuses on this statement that gender choice has no effect. And I want to compare that with an actual value. If gender choice has no effect, what does that mean? What would you expect to be the percentage or the proportion of girls being born? About 50%, right? So if gender choice has no effect, then what we can say is that the proportion of girls being born is 50%. Okay? So that's our first step. We can also think of this as having an effect. That could be a different claim. We'll think about that a little bit later on. But for now, this is a good start. So in this chapter, your claim is going to be about a population proportion compared to a value. the population proportions, or parameters, sorry. Parameters that we studied last chapter were proportions, proportion. We studied means, and then we also studied variances. And when we studied variance, we kind of scooted that over and say, oh, what if we just took the square root? Then we're essentially studying standard deviation. So I'll put variance / standard deviation. So your claim will have something to do, in this chapter, your claim will have something to do about a proportion, a mean, or a variance, or a standard deviation. Which means when you set this up, you can write this in symbols, right? So P is equal to 0.5. So that could be our first step. All right, so this is where the recipe part comes in for your hypothesis. So your claim can eventually be written as a mathematical statement with a population parameter set equal to, not equal to, bigger than, less than or equal to, one of those symbols equal to a specific number. And so what we're going to want to do with that is find the mathematical opposite of your statement. So in our running example down here, what would be the mathematical opposite of P is equal to 0.05 or 0.5? Not equal to, right? So that's going to be our mathematical opposite. P is not equal to 0.5. Okay? So step 3, once you figure out your claim and then your mathematical opposite, one of those will be labeled as your null hypothesis. So what we're going to do now is identify two statements. Well, we have two statements already identified, and they're complete opposites of each other, right? What we're going to do is we're going to place those two statements into two categories. One of them is going to be the null hypothesis. The other one is going to be the alternative hypothesis. The null hypothesis is going to contain a condition of equality, something with an equal sign. The alternative hypothesis will be the other statement that does not have an equal sign. These will be our symbol for null hypothesis and alternative hypothesis. So your null hypothesis will be labeled H H sub 0 So your null hypothesis will be labeled H sub 0. Now, between the two statements that I have up there, which one is the null hypothesis? The first one. That has a condition of equality. And then the second one is going to be called the alternative hypothesis. And this one will be labeled H. Well, in some places they have H sub A, but in our book we have H sub 1. They have H sub A for alternative, but for our case we're going to label it H sub 1. And so your null hypothesis has a condition of equality. Your alternative hypothesis will be the other statement that was brought up. And we'll label it H sub 0 and H sub 1. Is that good so far? So that is the first big step, is to make your hypothesis. All right? Whew. Now, testing it. We're going to test our hypothesis. Now, when you test it, remember the name of this is called a hypothesis test, but they also had another name. What's that called? Significance test. The idea behind calling a significance test is you want to, kind of want to identify how significant is it. And so what you need to do is you need to find some sort of a marker to identify what you mean by significant. Do you want it to be really significant? Like, do you want it to be really precise? And for cases where you're testing drugs and things like that, then you probably do want it to be a precise study, versus maybe you're just testing some social attitudes about things. And in some of those cases, you might not care so much about precision in your significance. So you want to identify a significance level. And sometimes that significance level is a lot of times given to you. And that significance level a lot of times is, not a lot of times, all the time is called alpha. You guys know that, right? You guys familiar with alpha, right? We did talk about this already. Alpha is some sort of measure that they have for, the 1 minus alpha business for confidence intervals. They talk about degree of confidence. Well, here it comes in a lot more formally in a hypothesis test, because that's the measure of significance. And alpha has a special probability and statistical meaning when you're doing significance levels. So in our class, if alpha is not given, assume to be 0.05 is going to be our default alpha. Okay? So we're going to test it. We have to find a measuring stick to test it against, and that's your significance level. And now we have to collect information. So what we want to do now is we want to read through our problem and find the important statistics that we will need to use. And in doing this, what we're going to do is we're going to collect statistics and then use a special formula. I'm trying to think now if it's in step 5 or step 6. I'll just say it's in step 5. We're going to collect statistics based on the sample, and that should be given in the problem, to use in a special formula. So we're going to collect statistics from the sample, and then we're going to identify a formula, and that formula is called a test statistic. Statistic. And depending on the particular scenario you're dealing with, you're going to be dealing with different test statistics. In this problem that we're working on, we're dealing with a proportion. So there's a special test statistic for proportion. In another problem that we might be dealing with, we might have a special test statistic for the mean. And then we will have a special test statistic for the standard deviation and variance. So depending on the scenario that you're working with, you're going to have a different test statistic. Okay? And you have to identify the test statistic. And so in this case, we'll assume that our alpha is equal to 0.05. And so this is one of those things where I have to fill in the whole mean for the moment. I'm just going to tell you what the test statistic is that you're going to use, and then we're going to figure out how to collect our statistics. So the test statistic that we're going to use is this special formula. And what it's equal to is going to be important for us too. So I'll say Z is equal to, and you'll have to remember that Z, wait, what have we used Z for? Z-scores, right? So this Z is actually going to be a Z-score for us. And other test statistics will be called T. When did we use T before? Student T, that Irish guy, right? The Guinness guy. So we're going to be using a T statistic, and then we're going to be using, what's the other distribution that we worked on? Oh, no, it was on videotape in my office. We didn't talk about it in class, but yeah, so what was the distribution for the standard deviation? Do you guys remember that? Chi-square. There's a distribution called a chi-square distribution that will be important also. So our test statistic is going to be, for this particular scenario, this is going to be a Z test statistic. So the test statistic is going to look like this. Well, don't worry about where this comes from. Just assume that this is going to be, well, I was going to say something that you would memorize, but you don't even have to memorize it because you guys get a sheet of notes. Oh man, I don't remember. It's P minus P hat. Sorry, I'm going to have to cheat. P hat minus P. So I was going in the right direction here. Is this a hat? No, that's not a hat. I need a hat. P hat minus P divided by the square root of, oh boy, P hat, Q hat, PQ. PQ divided by N. It's getting harder and harder to see here. It's getting smaller. So this is going to be our test statistic for this particular problem. Okay? Which means we have to look at this problem and identify P, P hat, P, and Q, and N. Oh. Let's start with P. What do you think P is equal to? 0.5. Where did you get that? It's what? The null hypothesis. They have P there already. That's where P hat comes from. Or, sorry, that's where P comes from. So we got P. Down here there's a Q. If there's a P, then there's a Q, right? 1 minus P. Q equals 1 minus P, and P is 0.5. So 1 minus P is also 0.5 in this case. N. What is N? 100 babies, right? We got that as an important piece of information from the original problem. So N equals 100. What's left? P hat. What's P hat? 97 out of 100. Where'd you get that from? The sample. Remember, P hat is a proportion in your sample. P is your proportion for the population. P, we actually don't know what P is. We're just kind of guessing. This is where you're making the hypothesis. You're saying, oh, the hypothesis is that P is equal to this. You don't really know that. That's what we're testing. Okay? But you do know what P hat is, because that is supposed to be the proportion for the sample. Just to be absolutely clear about this, it's based on this idea of the binomial probability. This is the number of successes that you're looking for. So X is the number of successes that you found in your sample. And in this particular scenario, a success is having the girl. How many girls do we have? we had 97 girls. So that's our X. Our N is 100, so our P hat is 97 over 100. Okay? Now that we have that, we should be able to fill in this formula, right? Hopefully. Oops. So should we do this? Why don't you guys, can you guys just do it in your calculators and tell me what the answer is? We'll wait for a confirmation. We'll have one more person say the same number, and if it's the same, then we're all good. I'll move on. Not that I don't trust you or anything, guys. It's a collaborative effort. Oh, since this is a z-score, we probably want to round it off to 2 decimal places. Just 40. Just need one more thumbs up on this. What do you guys say? Okay, be careful with the fractions, right? The numerator is a subtraction problem. So you want to make sure you either do that first, press enter, and press divide by the other business, or you can use parentheses around the numerator. Just be careful with that. Right? Okay, awesome. All right, so this is our test statistic. So based on this test statistic, what we're going to do, that's our step, we're our step 5 now, and we're going good so far. In step 6, what we're going to do is we're going to take our test statistic and see where that compares to. So this is going to be a little lengthy, this step over here. It's going to require a few things. We're going to need to find critical values. Remember that? And with a z distribution, we can either use table A2, which I don't really want you to use, or inverse norm in your calculator. So you know what critical values are. That's fine. I don't know if you know what one or two-tailed business is. So I'll just say it now, and we'll talk about one and two-tailed a little bit later on. And there's a really, really simple way to check whether something's one or two-tailed. So in our problem, it's going to be a two-tailed test. So I'll tell you how to get that. Actually, I'll just tell you right now. To figure out the tails, what you need to do is you need to look at your alternative hypothesis. Okay? Your alternative hypothesis dictates the tails. And for this not equal to symbol, you have two tails. If it's less than or greater than, yes, it's going to be a one-tail test. Yes. And what's really easy about that is that, well, I'll tell you later.
You ever have like a
Maybe. Yeah. Yes. Maybe. So at least is greater than or equal to. We'll talk about that later. All right. So we're looking at this problem. We've identified that this is a two-tail test. Identify whether it's one tail or two tail, and then now you're going to draw the distribution. So another keyword that comes up in hypothesis testing is the idea of a critical region. Have you guys heard of the critical region? So the critical region, this can just be a parenthetical statement. A critical region will be the tail. Whatever that means. And then after you draw the graph with the critical values and the critical region, you're going to put your test statistic in that graph. Yes. So the critical, if you have two tails, then your critical region will be on both sides of your graph. If it's one tail, then it's going to be on only one side. Now, which side is it going to be on? It depends on the tail. All right. So let's see if we can follow step 6 now, find the critical values and stuff like that. So critical values. I think we call it Z sub alpha over 2, something like that. Remember that? So with alpha, as 0.05, we have our critical values Z. .96. Remember that number that kept on popping up all last week? 1.96. Now we have to draw this. So we know that it's two-tailed. Two-tailed from the alternative hypothesis. So now we have to draw this. Because this is where I have to draw it. Because this is a two-tail, it has to go on both sides, right? And I know that 1.96 is on the positive side, and I know that this is a z distribution, which means it has a mean of 0 and standard deviation of 1. So that means the other tail must have a critical value of negative 1.96. And my critical region would be on the tails. Where's my test statistic? What is my test statistic? 9.4. That's way out here. I'll say TS for test statistic, and I'll remember that it's a z-value, and that it's 9.4, that it's way out here. And the most important part of this step is to identify whether this is in the critical region or not in the critical region. So based on my drawing and what you're seeing up here, is it in the critical region? What? Yes. Because it's on the tail. I guess I should just say it's on the tail, but they say critical region. So 1.96 is the boundary for the critical region. Anything that's greater than positive 1.96 and anything less than negative 1.96 will be considered in the critical region. 9.4 is a big number, and that is definitely in the critical region. The critical region goes on forever. Yeah, remember this graph goes on forever, right? So anything past 1.96 will go on forever. That's going to be part of the critical region. So our step 7 begins the decision-making process. So step 7, if the test statistic, that's your special formula, right, is in the critical region, then the wording here is important. We reject the null hypothesis. If the test statistic is not in the critical region, we do not accept it. We fail to reject. Hypothesis. So step 7 will be one of only 2 statements that you can make. You either reject the null hypothesis or you fail to reject the null hypothesis. What seems to be missing here? Accept? Don't use that word. What else is missing here? These two statements seem to be focused on the null hypothesis. It doesn't say anything about the alternative hypothesis. And that's another important aspect of this test. you don't get to say anything about the alternative hypothesis. Not in this stage, at least. So, you do not use the word except, and you do not use the word alternative hypothesis on this step. You either reject the null hypothesis or you fail to reject the null hypothesis. That's all you get to say. Okay? In our case, yes?
So say that our test statistic, let's just say got a number between negative 1.96 and 1.96. If it was within that, would that not be in the conclusion?
Correct. So if we happen to have landed here, our test statistic, then our test statistic is not in the critical region. Okay? Should I leave this here, or is that's going to be confusing? We'll see some more examples where we talk about the critical region in a lot more detail. All right, so step 7. Since the test statistic is in the critical region, what's our conclusion? We reject the null hypothesis. Okay? Now, this looks like it's the conclusion, but it's not quite the conclusion. So there's one more step left. And that is to interpret your conclusion in, they call it non-technical terms. So non-technical terms do not use the words hypothesis, null, or alternative. We want to use the original language of the claim. Or the original language of the problem. And for this one, it gets a little tricky to try to write it in non-technical terms. So the really nice thing about this is that we have a special chart, and all you have to do is know how to read a flow chart to make things a little bit easy for us. This is a table of formulas or a packet of formulas and tables that I think you guys might be able to use for the test. We'll talk about this when we get closer to the actual test. Or we'll be using this a lot ourselves. So this is the piece of the table that we're going to want to focus on for this last step. It's a flow chart. We start from the beginning, we follow through, ask ourselves questions, and then we see where we end up. So, in this flow chart that we're following through, we start, does the original claim contain a condition of equality? Oh, we have to look at our problem again. Original claim was in step 1. Does the original claim contain a condition of equality? Yes, it does. This one. So our claim was P equals to 0.5. Yes, it does. Did we, in step 7, did we reject the null hypothesis? Yes, we did. So step 1 and step 7 are the 2 steps that we're going to want to try to recall when we're going through this flow chart.
It was doing less than 0.5,
Then it would be going down here, yes. Or greater than. Yeah. So for this particular problem, we should be focused on this statement. Whoa, that's big. According to the statement, we should say something like, there is sufficient evidence to warrant the rejection of the claim that, what was the claim again? So I'd like to put P is equal to 0.05, but that's technical. It's not non-technical. So it looks like this was the actual statement. Either this or this. One of those two would work. I'm going to take the second one. That the proportion, you don't need to put that dot, dot, dot. Maybe I shouldn't put that dot, dot, dot there. That the proportion of girls being born is 50%. So that's rejected. So that probably means that this thing actually worked. So for this last step, for now, I'm just going to ask you to go at it blindly and just follow this flow chart. And the more you do this, and if you want to try to make sense of this in your head, then it will eventually start making sense. And they also have these comments on the side of the flow chart. There's 2 boxes where they have these special comments. This is the only case which the original claim is rejected. This is the only case which the original claim is supported. And you can follow those paths to see where it leads. Okay? The last box? There is not sufficient sample evidence to support the claim that, dot, dot, dot. So this is actually in your textbook. I pulled it out of the packet, which is also in your textbook. I can identify the page a little bit later on, but you can get this directly from the book. And I suggest when you are doing your homework that you have this table. It's a nice table to have around. Okay? All right, cool. That's our first hypothesis test. Now, you guys went at it with nothing in front of you aside from knowing. I think the only thing that you guys really knew about this information was Critical value. That's about it. And proportion means standard deviation, variance, and stuff like that. But yeah, aside from that, we kind of went at it. So there might be a lot of holes that we have. So at this point, what I'd like to do is I'd like to breeze through the PowerPoint presentation that I was initially going to show and just see if we can fill in the holes. All right? I'm not going to go through every single slide, or at least not focus on it, but there are a couple of slides that I want to highlight so that we can fill in the holes that we have here, and then we'll start doing more problems. So this is what they have in 8.2, and so they have a lot of definitions here. Oh, there's actually a couple of other things that we have to discuss, and we'll append our notes that we just created with our example. But now that we have seen a little bit of this, you know about the null and alternative hypotheses, you know about the test statistic, the critical region, significance level, the critical value. And so now there's a couple of things left for us to uncover, and then and we'll spend a little bit of time here. In fact, this I find is going to be an important a definition for us that is, one, used more popularly in statistical studies. And so when you read a statistical study, and in the statistical study they have some sort of hypothesis test, and they're going to give you the p-value. They're going to probably give you the p-value more often than they're going to give you the test statistic. But there is a relationship between the p-value and the test statistic, and we'll find out what that is. The type 1 and type 2 error just tells you, because this is based on statistics and probability, that this isn't 100% perfect. So there could be a slight error in this, and the error isn't an error like a mistake that we're going to have. The error that they're talking about here is the possibility that the statistics is wrong based on what you have. And I like to use the idea of convicting somebody as an example. We'll get there. All right. So they took this example a little bit differently from what we did. They took this example where they had a claim that p is bigger than 0.5. Our claim was p is equal to 0.5. Okay, so their example is a little bit different, and what I'd like you to do is try to encourage you to take a look at this in a lot more detail so that we can you can do a comparison. And they did some analysis using the binomial distribution, and they actually approximated the normal distribution with that. And these observations, if you, again, you'll look at it later if you look at it later, is based on our discussion earlier about the difference between having 52 girls versus 97 girls. So these are the components that they discussed. The null hypothesis, as a definition, is going to be the statement that that contains a condition of equality. Is equal to some claimed value. So the thing to remember here is that it contains a condition of equality. And then the other thing is that if you remember our conclusions, we only have two conclusions. We reject the null hypothesis, or we fail to reject the null hypothesis. In a formal hypothesis test, we're actually testing the null hypothesis. That's why at the end we don't say anything about the alternative hypothesis, is because the whole purpose in this test is to try to reject the null hypothesis. So we either reject it or we don't. Okay? So that's the story behind the null hypothesis. But again, the thing I want you to remember is that the null hypothesis contains a condition of equality. Okay? So in our first three steps, right? The claim, the opposite of claim, and then put those two things in one of these slots. The null hypothesis and the alternative hypothesis. So if the null hypothesis contains a condition of equality, then the alternative hypothesis is the opposite. So the alternative hypothesis must not contain a condition of equality. So in math, there's only three possible symbols for that. It's either the not equal to symbol, the less than symbol, or the greater than symbol. How about this symbol? Greater than or equal to, it contains a condition of equality. So maybe I should put that symbol on the previous page. When I say it contains a condition of equality, your possible symbols to use for your null hypothesis is either an equal to, a less than or equal to, or greater than or equal to. Now, these three and these other three are the only 6 possibilities we have when we're comparing things, right? So we've essentially exhausted all our possibilities for comparing a parameter with a numerical value. So 3 of them go to the null hypothesis, these 3 go to the alternative hypothesis, and they're going to get paired up. So there's 6 possibilities, but really when we're pairing this up, it only comes down to just 3 possibilities. Let's take a look. Oh, this is an exam question that nobody ever gets. So if you want to write this down, you can write this down, put a star on it, and then I'll try to remind you every now and then when we're doing a hypothesis test. So what does it say? If you want to form your own conclusion, if you're conducting a study and you want the hypothesis to be supported, to support your claim, then you must write your claim so that it becomes the alternative hypothesis. When we did our problem, we had our claim to be P is equal to 0.5, right? In our example. P is equal to 0.5 eventually became our null hypothesis. And so, because of that, there was no chance for us supporting our claim. So, the thing I want you to do is look at this word support and look back at that chart that I showed you. And in this chart that I showed you, try to see out of these 4 boxes where they have the word support. The first 2 has reject, and the last two have support. Okay? So, see, it's called the final wording flowchart. So the final wording flowchart has two boxes where they have the word support. And try to trace that back to the first step in that flowchart. Okay. This is the first three steps in identifying your null hypothesis and the alternative hypothesis. And you don't have to write this down because it's more or less the first three steps that I wrote down in my sheet. And this, I tried to follow their 8 steps, and so these are the 8 steps. So identify your claim, find the opposite of the claim, and then identify H1 and H0. Okay? So that's our first big step. Now, I like these next few slides because it focuses on something where they have problems. They don't ask you to go through the whole hypothesis test. They just ask you to go through it and identify the first 3 steps in your hypothesis test. So let's take a look at it one by one. The proportion of drivers who admit running a red light is greater than 0.5. So what is the parameter we're testing? What? Well, that was a couple of steps ahead from what I was thinking. But let's write down the claim. What is the claim? The proportion of drivers who admit to running red lights is greater than 0.5. So a couple of things to take note of. Some of the key words, and especially in this chapter, we're dealing with only 3 things. We're dealing with either a proportion, a mean, or standard deviation / variance. Okay? So those are the only possible scenarios that we have for this particular chapter, and you want to identify that from the beginning so that you know what variable to use. So proportion is a key word. Greater than 0.05, well, that's the other part of the key word. And so if you put those together, you have P is bigger than 0.5. And that's your claim. What's the opposite of the claim? P has to be exactly opposite. If I say less than, it's not quite opposite. What's missing? Less than or equal to. It has to be complete, right? Exact opposite. If you say P is greater than, P is less than, then there's, what if it's equal to? That's not being accounted for. So we want to make sure everything is accounted for. So this less than or equal to is an important part of this. And now that you have that, you get to put it in one of these slots. Let's take your claim. Where does your claim go? Does it go in the null hypothesis, or does it go in the alternative hypothesis? It goes into the alternative hypothesis. Why? It does not contain a condition of equality. Because you want to be supported. Well, that's dependent on the problem. So if the problems aren't always like this. But yeah, that's another good point. So in this case, what we're looking at is whether the claim contains a condition of equality or the claim does not contain the condition of equality. Here, the claim does not contain a condition of equality. does not. And for that reason, he goes into alternative hypothesis, which means the other one must go into the null hypothesis. Okay? Does that make sense? Let's try the next one. The next one, the mean height of a professional basketball player is at most 7 feet. At most. That's a tricky phrase, at most. At least I can highlight mean, right? And I'll highlight at most 7 feet. So I'll get this started. I know that my claim is going to be what? Symbol. The first thing is a symbol. What is it? Mu, the mean. Okay, so that's the first important part. You're dealing with a mean, so it has to be mu. Now, I know the other side is 7, at most. At most 7, what is it? Less than or equal to. So that one contains a condition of equality. So if that's our claim, what's the opposite of the claim? Strictly greater than 7, right? And then from here, well, you can tell which one has the condition of equality and which one does not. Okay? This is kind of fun. All right, one more. Standard deviation is equal to 15. What's our parameter we're testing? Sigma, right? And is equal to 15. Well, that basically does it. Claim sigma equals 15. Opposite, not equal to. So you can just identify your null hypothesis and your alternative hypothesis from here, then you're all set. By the way, because in step 7 we have to identify if our claim contained a condition of equality. Yeah, well, I'll leave it at this.
Is it opposite?
No, the null has to contain a condition of equality.
Oh, never mind.
Null contains a condition of equality. Okay? All right. So we talked about the test statistic. Whoa. We used the first one already, and here are the other two. So they will be important, maybe, but I'm going to skip over this, okay? Critical region, critical value, I talked about that, so I'll skip over this slide. Left tail, right tail, we talked about that, but we only give an example of two tails, so I do want to have you focus on these next couple of slides. So the idea behind figuring out a tail is to look at your alternative hypothesis. Your alternative hypothesis tells you the tails. So if your alternative hypothesis has a not equal to, as in the problem that we did earlier, this is going to be a two-tailed test. So the other only two choices for your alternative hypothesis would be a less than or greater than, right? Which means they're going to be one tail. If they're one tail, you need to figure out whether they're a left tail or a right tail. Because you need to figure out which tail to shade. You have two tails here. If it's a one tail, then you're either going to shade the one on the right or the one on the left. And easy way to do this is to look at which way your alternative hypothesis is pointing. If your alternative hypothesis is greater than, it points to the right, it's going to be a right tail test. If your alternative hypothesis is a less than, it points to the left, and it'll be a left tail test. I wish we had this all in one slide so you can do the comparison, but here's the other one. Left points to the left, left tail test. All right, it's past our break time, so we need to stop here. The rest of the steps, I think that was described well enough that I don't need to show you any more slides. I think the thing to do for us is when we get back, we'll talk about the p-value, the errors, and then we'll do a bunch of examples. All right, let's take a break.